Okay, so welcome back. Happy New Year. Your first video of the new year, so let's start it off right. We're going to combine video number 2 and number 3 together into one. So we're going to talk about square roots, which should be mostly review because you did these last year in geometry, and we're going to talk about the introduction to imaginary numbers. So let's get the square roots done first. We all know that the square root of 4 is 2, and the square root of 16 is 4. Okay, but what is the square root of 27? The square root of 27 is 5.196 because we always round to 3 decimals, okay? From here on out, we're rounding to 3 decimals because that's what the College Board wants us to round to. But what if I said I didn't want it approximately? Because remember, this is approximately because I'm a rounding. Approximately because I'm a rounding. Yeah, that made sense. So this is an approximate answer. What if I wanted an exact answer? This is where last year you learned how to simplify square roots. And there are 2 different ways to do it. I'm just going to teach you, actually I'm going to show you both first. So square root of 27, I know I can turn into the square root of 9 times the square root of 3. The square root of 9 is 3. The square root of 3 can't be simplified. So I could do it that way. But I think the better way to make sure that everything gets pulled out is to do an upside down factor tree. So 3 goes into 27 9 times. I'm going to divide again. 3 goes into 9 3. In a square root, okay, that is implied right there, that it's a 2 in there for a square root. I'm looking for groups of 2. So there's one group of 2. If I have one group of 2, 1 3 comes out. This guy doesn't have a partner, so he doesn't make a group, so he has to stay in. Let's try that again with square root of 320. Now, looking at that, I don't know what the largest perfect square inside is, which is why I don't like to teach this way. I would prefer you do an upside down factor tree. So I'm going to upside down factor 320. I'm having trouble speaking today. That's 160. I'm going to keep dividing by 2 until I can no longer divide by 2. Well, there we go. And 5 is a prime number. So you factor tree all the way down until you have a prime number and you can't divide by anything but 1. Sometimes 2 isn't going to work, so you try 3. I'm now going to look for groups of 2 numbers that are the same. These happen to be the number 2, so saying groups of 2, I'm looking for pairs, okay? There's 2, 3 pairs. So 3 2's, since that's what the pairs are, get to come out. So a 2 comes out, a 2 comes out, a 2 comes out. This 5 guy here on the bottom doesn't have a partner, he doesn't have a pair, so he has to stay inside. 2 times 2 times 2 is 8, radical 5. If I wanted to check it, what I could do is I could actually put this in my calculator, square root of 320, and square root of 320 will get me 17.889. And then I could put this in my calculator, 8 square roots of 5, and that also gets me 17.889. Simplifying a radical from this to this is no different than simplifying a fraction like this to this. Mathematically, these have the same value. This is just the simplified version. Mathematically, these have the same value. This is just the simplified value. So let's talk about operations with square roots. Square root of 2 plus square root of 3, you're not allowed to add them unless the underneath the square root looks exactly the same. The 2 and the 3 are not the same, so this is not possible. So if we look at the next example, square root of 2 plus square root of 3 we know isn't possible, but subtract the square root of 3 square roots of 2. Square root of 2 and square root of 2, these match. So I can do 1 square root of 2, subtract 3 square roots of 2, and I would actually end up with negative 2 square roots of 2. Now, this guy right here doesn't have anything to add or subtract, so I just keep him plugged on the end. So that would be my final answer. What about multiplying? Well, don't forget that outside the square root is a 1, so that's a negative 1. When I'm multiplying, only outside square roots can talk and inside square roots can talk. They can't talk to each other. So when I multiply, I'm going to multiply 6 times negative 1 and get negative 6, and then 2 times 5 and get 10 under the square root. What I would do then is look to see if that 10 can be simplified any further, and that cannot be simplified any further, so that would be my right answer. Again, if I put this side in my calculator and press enter, and put this in my calculator and press enter, they should give me back the same values. Now, what about this one? I just told you that square root of 7 and square root of 28 must match in order to add or subtract. It doesn't matter in multiplying, but to add or subtract, my square roots must look alike. These don't look alike, so you would think I'm done. Well, let's just look at 28, and let's just see what happens if we simplify it. 2 goes into 28 14 times. 2 goes into 14 7 times. And now I'm to all prime numbers. And a square root, again, I'm looking for groups of 2. There is a group of 2. So one group of 2 gets to come out. So this guy will change to minus. One group of 2 comes out. The 7 has to stay in. So I'm now at square root of 7 minus 2 square roots of 7. Sorry. And now my underneath the square roots match. So I can do 1 square root of 7 minus 2 square roots of 7, and that would equal negative 1 square roots of 7. Or you could just write it the negative square root of 7. And again, if you put your original problem in the calculator and pressed enter, it would give you a decimal. If you put negative square root in the calculator and pressed enter, it would give you a decimal, and these should match. Let's just separate these problems a little bit. Now, can we divide square roots? If you remember from geometry last year, you should right now be saying, oh, Mrs. Irwin, you're not allowed to have a square root in the denominator, because we did this last year in geometry. So in order to get rid of a square root in the denominator, I do something called rationalize. To rationalize, I'm going to multiply by something on the bottom that will get rid of my square root of 3. So if I multiply the square root of 3 by itself, remember, I can multiply these two numbers, and I'm going to get the square root of 9. Well, what is the square root of 9? It's 3. But if I multiply by the square root of 3 here, I also must put it on the numerator and multiply it. What is the value of this? The value of this equals 1. I can multiply anything by 1 without changing its value. I'm just going to change what it looks like. So if I multiply 2 times the square root of 3, remember, the outside can't talk to the inside, so the 2 is going to say 2 square roots of 3. So this will stay 2 square roots of 3. Let's try another one. So let's try 3 over the square root of 6. We're going to multiply by square root of 6 over square root of 6. Now, the long cut is the square root of 6 is the square root of 36, which would end up being 6. Okay? What I want you to see is when you multiply a square root by itself, it always comes out of the square root as the number. In the top, I'm going to have 3 times the square root of 6. Now, remember what I said? Outside numbers can talk, inside and outside can't talk. So this is one term on the top and one term on the bottom. So I can simplify 3 goes into 3 once, into 6 twice. So my final answer is actually going to be square root of 6 over 2. Well, what about this? Okay, this is a problem where it has a square root in the denominator, and what you're saying is, okay, so what you just told me was just multiply by the square root over itself. But remember, if I multiply the square root over itself, I'm actually multiplying to both of these numbers. So I'm going to have to distribute the square root of 3 here and the square root of 3 here. So really quickly, if I distribute the square root of 3 to the first term and the square root of 3 to the second term, well, I just told you that if you multiply a square root by itself, it's just going to come out as the plain number. Did I get rid of the square root in the denominator? No, there it is, right there. So this is not going to work. We're going to multiply by something called the conjugate. A conjugate is going to be 1 and square root of 3 will stay the same, but that's going to be a plus. And if you remember when we were factoring perfect squares, x minus 3, x plus 3, these are conjugates. The x and the 3 stay the same, one negative in the middle and one positive in the middle. So notice this was a negative, so I'm just going to make it a positive. But if I do it in the denominator, I need to do it in the numerator as well. Okay, this is a little bit more difficult, so I don't want that. I want it to be black. So I'm going to distribute here, and then these are binomials, so I need to put parentheses around them. So if I multiply 2 times 1, I'm going to get 2. And if I multiply 2 times the square root of 3, I'm just going to get plus 2 times the square root of 3, because I can't talk inside and outside. In the bottom, I actually am going to, remember that word FOIL that I said I would never say, I'm going to FOIL, but I'm going to call it distribute. I don't like the word FOIL, so I'm going to multiply the 1 times the 1, and then I'm going to multiply the 1 times the radical 3. And then I'm going to move to this next term, and I'm going to multiply negative 3 times 1 and negative radical 3 times positive radical 3. So a negative times a positive is going to give me a negative, and radical 3 times radical 3 gives me 3. Let's do the shortcut. You could go to radical 9, but that would just give me 3. In the numerator now, those two are not like terms, so I just get 2 plus 2 radical 3. In the denominator, I have 1 and minus 3. What happens to these two middle terms? Positive radical 3 and negative radical 3 cancel out, thus getting rid of my radical in the bottom, and I'm just left with 1 minus 3, which is negative 2. I'm going to rewrite this as this guy and this guy. Okay, there are two terms, so I have 2 over negative 2, and I have plus 2 radical 3 over negative 2. This will become negative 1, and this will become negative radical 3, negative 1 radical 3, because 2 divided by 2 becomes 1. Now, let's clean it up a little bit to make it proper math. Negative 1 plus a minus, I don't need, that's a minus. I don't need the 1 outside multiplying, so this would be my final answer. And again, if you went back to the original and put this in your calculator using alpha y equals, and this in your calculator, they will give you the same value. Let's try one more that looks a little ugly. Again, I just care that there is a square root in the denominator. I don't care what the numerator is. I'm looking at the denominator. I'm going to rationalize the denominator by multiplying by the conjugate. The conjugate of this is the 2 and the radical 7 stay the same, but if this is positive right here, it becomes negative here. The numerator must be the same that I just wrote in the denominator, because this value has to be 1. These cannot be different because a numerator divided by the same denominator gives me 1. Just like we said before, these are now binomials. So now I'm going to have to distribute out in the numerator and the denominator. So 1 times 2, 1 times negative radical 7, radical 2 times 2, and radical 2, so when I multiply positive radical 2 times negative radical 7, a positive times a negative will give me a negative. And then underneath here, I can multiply those and I get square root of 14. In the bottom, I'm going to multiply out. And I want you to remember that square root of 7 times square root of 7 just gives me 7. Positive times negative gives me negative. Okay? In the numerator, is there anything that I can combine? Do any of these look the same? No, they don't. If I look at 14 off to the side and I try to factor tree it to simplify it, here's prime and I don't have any pairs. So this will not simplify. So my numerator, as ugly as it is, stays 1 minus square root of 7 plus 2 radical 2 minus square root of 14. In the denominator, this negative 2 square roots of 7 and positive 2 square roots of 7 cancel, leaving me 4 minus 7 on the bottom. And I actually am going to leave that answer like that. If you wanted to, there are 1, 2, 3, 4 terms. Terms are separated by addition and subtraction, divided by one denominator. So I could do 1 over negative 3 minus radical 7 over negative 3 plus 2 radical 2 over negative 3 minus radical 14 over negative 3. That would become a negative. Sorry, a negative divided by a negative is a positive. A positive divided by a negative is a negative. And this negative divided by a negative turns into a positive. Before we move on to imaginaries, I'd like you to write down these 6 problems, and I'd like them worked out before class tomorrow. You will be handing these in, and we will go over them in class. So what is an imaginary number? Okay, so in Algebra 1, you learned about number sets. Okay, and you learned that there's a real number set that's divided into 2 groups. One is, let's put reals outside. One is called rational numbers, and one is called irrational numbers. Irrational numbers are ugly decimals, like pi, like square root of 5, like square root of 32. They just, if you put them into your calculator, they're just ugly numbers. Rational is anything that can be made into a fraction, ratio, fraction. So 1/2 is a rational, -5 can be made into a rational by putting it over 1. Square root of 4 is rational because that's actually 2. So those are pretty numbers. 0 is a rational number. 1 is a rational number. 3 over 7 is a rational number. Well, what happens with imaginaries? Completely outside of the reals are these things called imaginaries. Imaginary numbers. Why do we need imaginary numbers? Well, there are many reasons, but for what we're doing right now, let's consider quadratics, and we talked about this today. We crossed about where a quadratic crosses the x-axis is a real solution because it hits the x-axis. Even if it only hits once, it still has a real solution. That, remember, would be called a double root. But what if I had a quadratic that looked like this? Will it ever hit the x-axis? or like this? Would that ever hit the x-axis? Those are never going to hit the x-axis. So you would think that you would say they don't have a solution. Well, they do. They have imaginary solutions. So these two guys right here have imaginary solutions. What is an imaginary number? We just finished doing square roots, so if I put in the square root of 4, it's going to be 2. If I put in the square root of 9, it's going to be 3. If I put in the square root of 27, it's going to be that 5 point whatever number. If I put in the square root of negative 4, my calculator is going to give me an error that says no non-real answer. Well, what does that mean? If something is non-real, it is imaginary. But we have to be able to write that number somehow. So here's how imaginaries work. See that little negative in here? It just comes outside and becomes an I for imaginary. And if you look above your decimal point on your calculator, so if you look second decimal, you're going to see a little teeny I. That's our imaginary numbers. So what happens to the square root of 4? Well, the square root of 4 is still 2. So it becomes 2I. So square root of negative 9 becomes, the square root of 9 is 3, the negative becomes I. The square root of 27 negative becomes 5 point ... I. Okay? If we were going to keep it exact, remember we did this back on the first page, it would be 3 radical 3 and then put that little I right in there. Right in between the whole number and the square root. Right in there. Okay. So real quick, this little guy comes out as an I, 16 is a 4. This little guy comes out as I, but the square root of 5 can't be simplified, so it's just going to stay the square root of 5. Notice the order that I'm putting these in. Here's my whole number, my coefficient, my coefficient. Here's my imaginary, and then after the imaginary comes the radical. Square root of 60, so I'm going to 15 can only be divided by 3 now. Okay, so again, I'm looking for a pair. So here's a pair of 2's. So 1 pair of 2's comes out. 3 times 5, they don't have pairs, so they have to stay in. No negative, so it just stays 2 radical 15. This guy, the I comes out. Now, 252, divide by 2. Keep dividing by 2. I don't think that will divide by 2, so I'm going to divide by 3. I'm going to divide by 3 again. Now I'm looking for pairs of numbers. Here's a pair. Here's a pair. So 1 pair of 2's, so a 2 gets to come out. 1 pair of 3's, so a 3 gets to come out. 7 doesn't have a pair, so he has to stay in. I multiply the 2 times 3, leave the I, square root of 7. Unfortunately, this is not, you cannot check this in your calculator because you can't put this in because I get non-real answer, error. So you can't check an I in my calculator. What I can do is put square root of 252 in, 6 square roots of 7. So avoid the I. Just see if these have the same value. I know all the I stands for is that negative. So that's how you could check it. I'm sorry the video was so long. See you in class.